Now let us look at another important method, which is called load balancing method. It was actually proposed by a famous engineer T.Y. Lin. Okay. So he came up with the concept of equivalent load for simple analysis. So it greatly simplified how we can do analysis for even for an statically indeterminate systems. Okay. So the concept is very simple. By the virtue of the cable profile, I am not only going to generate a horizontal compression on the concrete, I am also going to generate a vertical pushing on the concrete. Okay. So that is what we are going to see. The external load is actually designed or balanced by the vertical force produced because of the change in the curvature of the tendon. So please note this. The vertical component will be generated only when there is a change in the slope of the cable profile. Wherever there is a change in cable profile, there a vertical component will come. When there is no change in the cable profile, only you will get horizontal component. But horizontal component, if it is at an eccentricity, it will create a moment opposite to that of action of your external loads, right. So that is the reason for a parabolic cable profile, you generate a uniformly distributed vertical load pushing the beam upward for a simply supported case, right. Now let us look at this very simple case. You have a linear profile of a cable which is changing the slope at this point. Now again we are looking at this beam which is having a cable profile with this kind of a profile. Now let us look at what is again this is simply supported example, which for simplicity we have taken. Now if I take a small elemental length of this strand or PT cable between A and B, and I look at what are the forces that it is generated. Now you see that the tendon or the P-stressing cable will always be in tension. So if I look at the free body diagram of only that cable, I am generating, let us say, this pre-stressing force P again, which is equal to, let us say, 75% for characteristic strength and multiplied by AP will give me what is the force that is there. Now if you see here, this is actually producing with respect to horizontal some cable angle theta, right. So you will find that this P will have two components, which is P cos theta and P sin theta. Okay. So similarly on this side also, equilibrium has to be satisfied. Both horizontal component, vertical component, everything has to satisfy. So equilibrium always has to be satisfied. This is the free body diagram of the pre-stressing cable in the portion AB. Now cable is in tension, but what is the net effect it is producing on the concrete on the segment AB? That is what we are looking, because they are all connected together, right. So at this location, if you look at it on the concrete, you will have exactly opposite to that of what you have it on the two sides from steel cable. So you will have P sin theta and P cos theta, right. So if you look at this section, you will say that there is going to be P sin theta which is acting, and similarly P sin theta, it is acting like this, right. So this is the free body diagram. So this is the way that I am going to push the beam upward. Okay. So this is the forces that are acting on the frame. So we are interested in what is the effect of pre-stressing on the concrete. Okay. But overall, if you look at it, they will balance. It does not mean that concrete does not feel the stress. Okay. They will balance, equilibrium has to satisfy, but it is still feeling that force, right. So you have to see that. Okay. Now let us look at what is happening at, this is at the location A and B. Now let's look at the same thing, what is happening between the segment CD, right. Okay. Now you see here, if you go back to the previous one, you see the net force, if you look at it, P sin, everything is in, it has to be in equilibrium, right. Now let's look at what is happening in this segment C and D. Okay. In this way, if you look at it, at this location, when you look at it, both of them will produce, if you look at the free body diagram between C and D, the net effect is actually is going to be on the concrete is going to be, you will have P sin theta, they will not balance, it is going to push up like this. Okay. So if you look at this segment, if you look at it, you are going to have 2 P sin theta that will be acting on that element. So that is what, if you assume this entire beam to be a linear element in a simple line, and these are the net equivalent load that is going to be acting on the concrete. Okay. So this is the, we looked at this, right. So, this is the net. So, this 2p sin theta will come when the cable is changing the angle. Okay. Here it is linear, but there is no slope change. But here if you look at it, there is a slope change of 2 theta. Okay. So, this is theta and this is theta. So, the net slope change, if you look at it, it is going to be 2 theta, right. So, that is the slope change. So, the vertical force is going to be the slope change multiplied by the p. Now, we know that when theta is small, right, sin theta can be approximated as theta, right. So, that is what you can write this simply as 2p. So, when you simplify that, you can simply write that as p theta when theta is small, and this will become 2p theta, and this will also become p theta. Now, p cos theta will become p, because when theta is small, cos theta tends to become 1. So, you can write. So, that is the reason the net horizontal component will be very close to that of the pre-stressing force, but the vertical component can be quite significant. Even though the theta may be small, but this component can be, the vertical component it is producing is going to be significant, which is quite beneficial for reducing the net effect of external loads. In addition to that, the shear capacity also will be improved. So, we will see how do we do that. So, this is the, now if you look at the moment from the pre-stressing. So, this is the equivalent load. So, our goal is to produce this equivalent load. So, this is the key. So, wherever the slope is changing cable profile, that will create an vertical force. How much it will be vertical force? The change in the angle multiplied by the applied pre-stressing force, right. Okay. So, that is what we have. So, this also if you look at it from here to here, so p theta, that is the reason that we are getting. Okay. Okay. So, the tendon profile can be used for balancing a concentrated load acting at the mean span. Now, for small eccentricities, we have seen that sin theta can be theta. So, if you see this as eccentricity E, and if this distance is taken as L by 2, now this theta will be equal to E divided by L by 2, which is nothing but 2E by L. That is what we have got. So, the total W that can be balanced by this kind of a linear cable profile is nothing but 4 into, so because it's basically it's equal to 2 into P into theta, which is 2E by L, which is nothing but 4P by L. So, that is how we get your 4P by L, right. So, this is the way that we get your load that it can balance. So, that means pre-stressing is creating a 2P theta that is equivalent to 4 into P by L. Theta I am replacing in terms of E and L. Okay, now let us look at what is the equivalent load on the concrete produced from different cable profiles. Okay, this also we can derive, and this is a very common profile you have. Typically, cable profile will follow the bending moment produced by the external loads. Let us say for a simply supported case subjected to uniformly distributed load, you know that the bending moment profile is going to be parabolic. So, similarly, the profile of the cable that I need to follow also should be parabolic. So, this is a cable that I am taking. So, and I told you the vertical force that is put on the concrete is proportional to the slope change that is happening on the cable profile. Because it is a parabolic cable profile, the slope change is going to be constant along the length of the member. So, that is the reason you generate an uniformly distributed force that can be calculated as well. And at the top, at the bottom, when you look at it, again you have two components. If it is theta, you will have P cos theta and P sin theta at the bottom. So, this is an equivalent load. Okay. So, you can get that. And similarly, this W equivalent per unit length also we can calculate, which is equal to W equivalent, which is equal to basically 2P sin theta by L, if you take this as L. So, the moment from the pre-stressing will be exactly like this, okay, which is going to be, because it is subjected to uniformly distributed upward force. So, that is going to create a moment like this. Now, let us look at for a cable profile which is linear. There is no change in the cable profile, but it is always at an eccentricity of, let us see now what is it. So, you can see that simplified. If I look at it on the concrete, P, there is going to be a concentric force P. In addition to that, P into E, that eccentricity is always going to be there, right. So, the moment from the pre-stressing here in this case going to be, it is not going to change along the length of the member, it is going to be constant. You have already locked that P into E, which is constant along the, but there is no net vertical force per se, but it is also creating a camber upward, right. But that is come from the end moment that it is being created because of the eccentricity. Now, let us look at this is again another practical case. Now, instead of eccentricity at E, here in this case eccentricity is 0, here eccentricity some value is there, right, some value is there. And if you know the cable profile, I can calculate again what is the equivalent load, right. And in addition to that, you are also having a moment is also acting. Now, why is moment is acting? Because this is the force that it is acting. So, P into E still will be there on the concrete. So, P into E is the moment which is equal to P into E at the support. So, not only this is subjected to equivalent upward force, but there is also end moment, and this is a more advantageous system. And this is the bending moment profile that you will get from pre-stress. Now, next is a again another interesting case. Now, the beam is actually having this kind of a profile, right. So, and the cable is also following the profile, the CG of the beam. Now, you see here, if I assume this as a equivalent line element, and you will find that this is the internal forces that we are going to get, okay. Again, P sin theta, P cos theta, P cos theta, P sin theta, right, and this is, let us say, right. So, but if I take the cross section here, now the moment from horizontal component and the vertical component will balance each other. So, you will find that there is no moment from pre-stressing on the element will be 0, because it is a self-balancing system, but it is having vertical force, right. So, in this case the moment will be 0. So, these are very simple. This is a profile that we follow for a continuous beams, okay. So, always the eccentricity will be at the top, because you have to tackle the negative moment or hogging moment that it is coming. So, that is the reason we will have it here like this. Okay. So, now let us quickly go through an example problem, and let us see how to use the 3 concepts that what we have learnt in this lecture. Again, I am taking the same cross section 500 mm by 1000 mm I section with a web thickness of 150 mm, and with the area of pre-stressing steel is also given here, and it is subjected to, let us say, 100 kilonewton, and eccentricity is at a distance of 400 mm from 400 mm is given here. And what is that we are trying to see? What are the concrete stresses at mid span and supports at the top and bottom of the beam if the pre-stress only is acting, okay. First, we need to find the stresses based on SES concept, and the second one using equivalent load approach. That is a question A. And question B is what stresses result from superposition of pre-stress and self weight of 1.5 kilonewton meter. So, now we are also adding a self weight of 1.5 kilonewton per meter. They have already calculated the self weight, that is nothing but cross section area multiplied by the unit weight will give me what is the self weight per unit length, right. The area is given to you and you can assume self weight. So, that worked out to be 1.5 kilonewton per meter, okay. And the moment of inertia of all section also calculated, it is a symmetrical cross section with distance of top fibers is 500 millimeter, right. Now, let us quickly run through these numbers and see using this each method what do we get out of it. Again, it has been given pre-stressing force is equal to 670 kilonewton, area of concrete is 290,000 millimeter square, and eccentricity is 400, and these are the section properties that we have already calculated even in the last class. So, this is the same type of cross section we are going to use in further analysis also, so that you get an idea of the same properties. You don't need to calculate. Now let's look at now how to use the stress concept and find stresses at the support. Again, what are the, if you go back, this is a simply supported beam subjected to a point load, right? So 10 meter and Q 100 kN. So I have a load like this, right? Or P or Q, whatever it is, right? So you will know that, let's say it is also subjected to some self weight, right? For any case, for, let's say, for applied load or this, for this load we know that it is going to be, right. So this is the QL by 4, this is your bending moment diagram, right. At this location moment equal to 0 at support, right. So you will have force that is acting will be only the pre-stressing force. In addition to that, now again, why is it? If you go back in the cross section, what are the eccentricity that you have here? To see here, eccentricity E is equal to 0, here E is equal to 400. So that means only P will be there, P cos theta, theta will become small, so P will be equal to, P cos theta will be equal to P, and there is no, and the eccentricity is 0 here, okay. So the only there is going to be a pre-stressing effect only. So stress at the top and stress at the bottom is nothing but P by A, and that gives me a stress of 2.31 megapascal. Now how about stress at the midspan? Assuming that there is no self weight, right? You will have concentric component, okay, and then you will have moment due to pre-stress. Now moment due to pre-stress will be P into E. Now why is this is in positive? So that means the moment due to pre-stress is producing tension at top. We know that because pre-stressing is at the bottom. When I am pushing the beam up, I am going to have, I am basically making it in the a hogging, right. So it is going to have tension at the top. So that is the reason we are creating this, and if you substitute the value, you get stress, net stress of 1.48 megapascal only because of the applied pre-stressing, right. Now stress at the bottom, again both of them will be in compression, and you get a value of 6.1 megapascal, right. So now let's look at using equivalent load. Now using equivalent load, we have seen the net vertical force is equal to P into the net slope change that is happening at that point. At every other cross section, the cable is linear. Only at the midspan, it is linear and it is changing its direction. So net slope change, we calculate that is nothing but 4E by L and multiplied by P is the net vertical force that is acting at that location. So we can calculate, this is nothing but your 2P theta, and we calculated theta to be what? It is basically 2E by L, so into 2P, so that is nothing but 4PE by L, so that is what it is acting. And this is P cos theta, and it is approximately equal to P because cos theta will become 1, right. So then the vertical force has to be in equilibrium, that is going to be half-half, there is no other load that is acting. Now at supports, the concrete is in pure compression caused by force P cos theta. For small eccentricities, we can take cos theta equal to 1, and even in this beam, if you look at it, E is equal to 400 millimeter, right. You can calculate length is, we have taken it as 10 meters. So compared to the length of the beam, the eccentricity is so small, the slope is going to be small, so cos theta can be assumed as 1. So you can run the numbers very close to 1. So stresses at the support, again from this calculations, is only P is acting, so it is going to be P by A, which is 2.31 megapascal. Now at midspan, the moment that it is acting is because of this loading is going to be W into L by 4. We know for a simply supported beam subjected to point load. Now the load is this from pre-stress. This is the equivalent load from pre-stress, right, into L by 4, which is equal to P into E. So, P into E is the moment that is acting at this mid cross section, right. So, send the stress at the mid span at top, again you will have concentric component from pre-stress. Now, the moment that it is acting is P into E, right, and moment divided by section modulus will give me the stress. Now, here you do not consider the moment from pre-stressing again. So, you consider only the load effect, because that is what we are converting, pre-stressing effect is what we are converting in the form of a vertical equivalent load. So, you consider only the beneficial effect of horizontal component, and whatever that moment generated from the equivalent load, this is the moment from equivalent load, right. So, we have calculated this is moment from equivalent load, right. So, you substitute these values, you get 1.48 megapascal. Now, let us look at what is the stress at the bottom. Again it has to be same, it does not matter whether you do stress analysis or force analysis or equivalent analysis, everything will yield you the same, because they are all statically equivalent approaches. So, you will end up with same stress magnitudes. Now, let us go. Now, part B, what is the moment at midspan because of the self weight? And self weight is given as 1.5 kilonewton per meter, and we know L is 10 meters, so L square is 100. So, 1.5 into 100 by 8 will give me 18.75 kilonewton meter, and stress because of the moment is going to be due to self weight is m by z, which is only very small 0.26 megapascal. Now, resultant stresses, this is again from concentric pre-stress, right, and this is self weight, and this is from moment due to pre-stress. So, when you add all of them, principle of superposition is valid, again 1.22, and here it is negative 5.84, right. This is including the self weight. So, now you can see that the self weight is reducing the stress, it is making it more tension or reducing the net compression. Previously it is 6 point something, it has become 5.84, right. And at the top again it will try to reduce the compression that is available, right. Okay, it is going to produce compression, it is, if at all it is in tension, it will reduce the tension. Now, let us see what is the moment because of the live load. Live load we have given as 100 kilonewton. So, total live load moment is 250 kilonewton meter, and stress because of this moment is m by z again, which is 3.54 megapascal. So, when you add again the extra effect, this plus this is going to be negative 2.32 and 2.3. So, you see here nearly because of the live load, self weight and pre-stress, you kind of get stress which is nearly constant of 2.3 megapascal in this example, which is the entire section is subjected to only 2.3 compression for the given loading configuration. Now, let us look at the part D. Without considering the effect of self weight, find out the equivalent load from pre-stressing force that can balance the concentrated force Q. That means, I want to eliminate the effect of this Q, which is 100 kilonewton, right. So, which is basically, if you look at it, 4 into PE by L, the moment here is PE, right, due to pre-stress. So, how much it can balance? That Q will be equal to, QL by 4 should be equal to PE, or in other words, QL by 4 should be equal to P into E from moment from the pre-stressing. That means the Q that what it is can balance is going to be 4 into PE by L, right. So, imagine this is what we got, right. So, this moment we got that, right. So, basically we got this kind of an equivalent load, right. So, that load produces a moment of PE that should be equal to QL by 4, which is an external load that it is acting, and if you substitute that, you get Q equal to 104 kilonewton. So, we have applied only 100 kilonewton, right. So, that is the reason we can go up to 104 kilonewton. So, that means you are not going to feel the effect of live load at all. Okay. So, let us look at in grammatically what is happening. So, this is a concentric stress component which is negative P by A from pre-stress, everywhere it is going to be compression, and this is from pre-stress, hogging stress by pre-stress, that is going to create tension here, compression here, and it is going self weight, it is going to create compression here and tension here, and concentrated load of 100 kilonewton, if you look at it, it is going to create 3.54, which is going to be negative, and this is going to be positive. So, net if you add all of them, we have seen that pretty much the entire section is subjected to a stress of 2.3 megapascal. So, in this way I can play with the amount of stress in such a way that the bending effects are not there at all. The entire section is subjected to only concentric axial compressive stress. So, then if there is no tension at all, then there is no problem of cracking and there is no problem of serviceability issues, because pre-stress, if it is always going to be in compression, there is no problem. Concrete likes compression, right? So, there is no problem at all, right? Okay. So, let us summarize what we have discussed. So, we discussed the principles of elastic beam theory, and we also using three methods of analysis, three concepts: stress concept, C-line method or force method, and load balancing method. We saw different sections how to calculate the maximum stresses, and we also saw how to calculate the equivalent load using load balancing approach, and we also did one example of calculating stress analysis for a flange section. So, with that we will continue the lecture in the coming modules. Thank you.